Let's start it. So our second speaker for this session is Gerbai from the University of Hong Kong. Today he will talk about quantum causal unraveling. Gerbai, the floor is yours.
Yeah, thank you. I'm very happy to introduce here our new work on quantum causal unraveling. This is a joint work with Yadong Wu, Yan Zhu, Professor Masahito Hayashi, and Giulio Chiribella. Let's start with what this title means. Many natural processes arise from a sequence of basic interactions, but maybe we cannot access these individual events. This is a case for example, the scattering experiments in high-energy physics. The problem of quantum causal unraveling is to determine whether this natural process can be broken down into a sequence of simpler interactions. And if so, to determine the order of such interactions and determine which systems take part in each interaction. This is done by accessing only the inputs and outputs of the process, or black box accesses of the process, in the sense that we don't have the access to the individual events inside the whole process. This picture shows our problem. We have a physical process that is composed of some basic interactions. Each interaction involves a subset of inputs and outputs. This physical process is inside a black box, and we have only access to the inputs and outputs. Our objective is then to infer the structure of the interactions inside this physical process with only access to the inputs and outputs. The problem of quantum causal unraveling belongs to a larger problem called quantum causal discovery. And in causal discovery, the objective is to infer all causal relationships by observing the input and output systems. This field has been theoretically studied well by many quantum causal models proposed, for example, in these works. And on the algorithmic side, it has been studied not so deeply because only special cases involving a few systems and a few hypotheses have been studied. And this is, well, not surprising because this problem of quantum causal discovery is intrinsically hard. And the general case is even hard classically for classical causal discovery. However, there is still chance because in these works, quantum advantage has been observed. So we may use some quantum method to deal with quantum causal discovery. And in this work, we will consider the most general n input to n output case. And our objective is to produce the ordering of inputs and outputs. So it is like a subset of the full quantum causal discovery. But knowing the order itself is already quite important, because knowing the structure allows, for example, efficient tomography of the process. And from this, we can also model the underlying physical process from the observational data. And knowing the causal order allows us to represent the process efficiently with, for example, tensor networks. And this tensor network structure could allow many more applications, including efficient simulation, compression of states. On the other hand, for quantum networks, the quantum causal unraveling is also useful because in a quantum network, the signaling relations between inputs and output ports would indicate that data could be transmitted from this input to that output. So an efficient algorithm that detects such relations will be useful for quantum networks to detect the data transmission paths. This is especially important where, like when the network structure is dynamically changing, for example, a wireless network. Our main result is that we devise the first efficient algorithm for quantum causal unraveling. We consider two complexity measures for efficiency. First one is sample complexity, which is the number of black box queries to the quantum process C, and also computational complexity, which is the number of additional elementary quantum gates and classical operations. We propose two kinds of algorithms. Algorithm 1 uses quantum circuits, and it is efficient for processes with bounded information loss and causal feasibleness. We will show these conditions later. The second algorithm uses only local state preparation and measurements. This is kind of a less quantum algorithm because it is based on classical statistics. But it features a low sample complexity as low as O log n. But the benefits of this is at a cost of stronger assumptions. Before I go to the details of the algorithm and problem, we need some, we show the background knowledge for our problem. This is a quantum com. A quantum com is a model to model, is a model for ordered quantum processes or processes that has a causal order. A quantum com is a channel that can be written as the concatenation of n subchannels, where each subchannel is called a tooth of the quantum com. The channels are connected by memory wires or intermediate systems. This quantum com structure is general in the sense that any process that has a causal order can be represented with some quantum com. The quantum com structure defines a causal order between the input systems and output systems, as shown in the in this causal graph on the corner. AI could only signal to the output BI, where J is larger or equal to I, meaning that BJ is causally after AI. If a process C has this form, then we see C is compatible with the causal unraveling A1B1 to ANBN. With that, we can now formulate our problem. Our input is a black box access to quantum channel C with input wires A1AN to B1BN and output wires B1BN. The output will be permutation sigma and pi of 1 to n, such that the sigma indicates the ordering of the inputs and the pi indicates the ordering of outputs. We want an ordering such that C is compatible to this ordering, to this. So C belongs to com A sigma 1 pi 1 to A sigma n B pi n. This means that the quantum process can be decomposed into n interactions, and the ith interaction involves only A sigma A and B pi I. In this talk, I will focus on the case where each interaction involves only one input system and one output system. And the details for like more inputs and outputs will be in the paper, and I will not talk here. So let's go into our first causal unraveling problem algorithm. The algorithm is based on the following criterion for quantum comps. Let C be the choice state of the channel C, then the input wire AX and output wire BY constitutes the last choice of C if and only if this equation holds. The left-hand side of this equation, trace BYC, means the marginal choice state on all systems except BY. And the right-hand side is the tensor product of two things. The first one, trace AXBYC, is the marginal state except AX and BY. It's indicated by this box here. And the second term is a maximally mixed state on system AX. This equation in this tensor product form indicates that these two systems, AX and all systems except AX and BY, are independent. It means that, well, intuitively, it means that AX cannot signal to any systems that is before AX. So this has a causal order. So our first algorithm is based on this criteria, and it is a recursive algorithm. The first step is to enumerate an input-output pair AXBY and check with the criterion mentioned in the previous slide whether AXBY is the last tooth of this quantum column. And if we have identified that AXBY is the last tooth, we assign AXBY to the last tooth and remove it. By removing, I mean to feed AX with some arbitrary state and discard the output of BY. After removing this, the remaining process will be a process with n-1 inputs and n-1 outputs. And recursively, we apply this algorithm to the remaining column that is smaller. We do this recursively until we reach some bottom case. The efficiency of this algorithm is based on some assumptions. The first assumption is bounded information loss. It says that the cross rank of C is bounded by a polynomial of n. But the C is required to be put into some standard form. This is in the paper, and I will not show it here. The second assumption is causal faithfulness. It says there exists a number chi-mean that is larger than 0, such that for any two disjoint sets of wire S and T being tested for independence, either their correlation strength is 0 or their correlation strength is larger than this threshold chi-mean. The correlation strength we use here is chi1. It's defined like this. It's trace defined like the trace distance between CST and the CX tensor CT, where CST is a marginal state of C on systems in S union T, and CSCT are marginal states of C on systems S and T. This correlation strength measure, we call this the correlation strength measure because this measure is equal to 0 if and only if S and T are independent, meaning that CST equals CS times tensor product CT. So these two systems are uncorrelated. Given these assumptions, we can now give the theorem for the accuracy and complexity. Under these assumptions, for any confidence parameter chi 0 larger than 0, our algorithm satisfies the following conditions. With high probability, the output is a correct causal unraveling of the original process. And the number of queries to see is given in this equation. In this equation, n is a number of input and output systems, and RC is a cross rank of C. dA is a maximum dimension of input and output systems. And the chi-mean is defined in the previous slide, the correlation strength threshold defined in assumption 2. Note that this is polynomial in n and the dimension dA. The computation complexity is still have polynomial in n and dA. So we have given the the outline of this algorithm. But there is one thing that I didn't mention before is the first step. Well, how can we check whether AX and BY satisfy the criterion for the last tooth? We will do this in a sequence of reductions. The first step is to use the property of the criterion. If AX/BY is the last tooth by proposition 1, AX is independent with all wires except AX and BY. This independence can be then converted to the property that the following channel is a constant channel. Wire only AX, and all other inputs are fed with half of a maximally entangled state. On the output side, BY is discarded. So we can see from this circuit that if AX is independent with everything except BY, then this channel must be a constant channel. So we have reduced the problems to testing whether the channel is a constant channel. To do that, we do another reduction. To decide this channel, whether this channel is a constant channel, we check whether the output of the channel depends on the input. To do this, we pick a set of different input states. The first step is to pick such a set of input states that is informationally complete. Informationally complete means that psi alpha spans the linear space of all Hermitian matrices. And the second step is to compute the output of these input states. That rho alpha be the output of psi alpha. The third step is to compare those outputs. We pick rho 1 C is a constant channel. So the last step is to say how we can estimate those trace rho alpha, and these other terms. This is done by a circuit called the swap test. The swap test estimates trace rho sigma given copies of rho and sigma. It is composed of a control swap gate. The control qubit is initialized as a plus state, and the swap is applied on rho and sigma. On the output side, the control qubit is measured in the plus-minus basis. One can show that the probability of outcome plus is related to trace rho sigma. Therefore, by running this circuit many times, we can approximately compute trace rho sigma. And the equation is given here. So now we have completed algorithm 1, and here is a summary. We have algorithm 1, which is a recursive causal unravelling algorithm. This algorithm is based on the criterion for last tooth. And to decide the criterion of last tooth, we perform a sequence of reductions. We first reduce this to the independent test of two sets of wires, and we convert this independence test to the test of a constant channel. And to solve the test of constant channel, we need to compute the distance between the output states of the channel. And last, the distance between the states can be estimated via the swap test. As I mentioned before, there is a second algorithm that works with only local state preparation and local measurements. So in our case, this is how we do this local state preparation and measurements. We first pick an information complete state for each input wire and an information complete PWM for each output wire. We repeat the query to see n times, and in each time we generate inputs randomly from this input state set and measure the output with the PWM. In each time we would obtain data alpha 1k to alpha nk and beta 1k to beta nk, where alpha 1k to alpha nk are the labels of the chosen input states. Beta 1 to beta n are the measurement outcomes. We can arrange those data we get in a matrix in the lower right corner. And in each row, the matrix corresponds to one query to the process C, and each column corresponds to one input or output wire. There's a question in the chat, but I'll answer that later. When we notice that the informationally complete states and measurements we use here is enough for a process tomography, but we will show that the number of repetitions is far less than a full process tomography. Let's see how do we use this data we collected. For every input-output wire AIBJ, we take out the columns corresponding to AI and BJ. These two columns are the statistics for the marginal choice state CAIBJ. And with this information, we can perform tomographic reconstruction of CI and BJ. And thus, we can estimate the value of Chi1 AIBJ using this reconstructed state. Recall that Chi1 is a measure of correlation strength. So if Chi1 is smaller than the threshold, then we can say that AN and BJ are independent. We do this for every input-output pair, and we could obtain a matrix, independence matrix in the IJ from the data. And this matrix in the IJ is true whenever AI and BJ are independent. Let's see how we can use this in the matrix to perform causal unraveling. It is based on some assumptions, and the first assumption is like this. There exists a constant threshold chi mean such that for every I no larger than j, pi a sigma I b pi j is larger than chi mean. Well, to say this in words, it means that for every I no larger than j, the input of the ith tooth must be correlated to the output of the jth tooth, meaning that any input has a non-trivial effect on any output after it. With this assumption, we can give an efficient algorithm. The algorithm is like this. First, we obtain the matrix in the IJ from data using the method we introduced before. And for every input wire AK, we count the number of outputs that are correlated to AK. This number of outputs correlated to AK, we call it CAK, is the number of outputs after AK, because by our assumption, AK is correlated with every output after it. So we know that there are CAK outputs after it, and therefore there are n minus CAK outputs before AK. So we can conclude that AK must be the input of the n minus CAK plus 1 tooth. By this, we can order all the input wires, and in a similar way, we can order the output wires. This algorithm has a sample complexity given in the following formula. And we can see that the sample complexity is only logarithmic in n. Another case that can be solved by a similar method is a case where C is the tensor product of n channels. We can imagine, we can put it this way, like AI could only signal to one output wire, that is B pi prime I, where pi prime is some unknown permutation. To solve this case, we only need to determine which input is routed to which output. And the idea is to test the correlation between all the parallel input outputs and match correlated ones. So the algorithm is first obtain the independence matrix from data, and then match AI and BJ if in the IJ is false. In a similar analysis with a previous algorithm, if there exists some threshold chi-mean larger than 0, such that either the correlation is 0 or larger than this threshold, the sample complexity is the same as before. It's logarithmic in n. But in this case, we can give an additional guarantee to the error of our algorithm without defining such a threshold. This theorem says with high probability, our algorithm outputs a causal unraveling that is approximately correct, in the sense that C is the original channel and D is some channel that satisfies this causal unraveling, and the distance between C and D is small. We have used a diamond norm distance, which measures the distinguishability between channels. And in this case, we can see the complexity is still polynomial in n. So, to summarize, we have given efficient algorithm for quantum causal unraveling. The first algorithm is a swap test-based independence test. It is applicable to general causal order and is efficient for channels with bounded rank on causal feasibleness. The second algorithm uses only local state preparation and measurements. It is more experimental friendly since it uses only local operations, and it has as low as O log n sample complexity. But it can only solve some special cases, including every input is correlated to every output affiliate and the case of independent channels. The applications of causal unraveling algorithm includes efficient representation. With a given causal order, we can efficiently represent and perform tomography of the process and model the underlying physical process. Also, for quantum networks, such an algorithm is important because it can detect singular relations between transformation paths. I have mentioned that the quantum causal unraveling is kind of a partial solution to the more general problem of causal order discovery. To extend this work, we may perform more independent tests that is proposed in this work, and we may find out more causal correlations and build a more full causal order discovery. However, the quantum causal discovery is generally hard, and the general independence test is also hard. So as a future work, I'd like to mention two questions. First, how far can we go with an efficient causal discovery algorithm? And the second one is, because classical machine learning has been used for classical causal discovery, can we also use quantum machine learning for quantum causal discovery? Okay, and this closes my talk. Thank you. Okay, there's a problem in chat.
Yes.
How no definite causal order can be detected in the settings. Well, if the process doesn't have a well-defined causal order, the algorithm will just stop and say there's no such paralleling.
Okay.
Yeah.
Thank you, Gerbai, for this very wonderful talk. Is there any questions from the audience?
I wonder, can you hear me?
Yes.
Yes.
I was wondering, you defined partial trace of comb as inserting random state and partial trace it out. Is it, why do you think this, I mean, the best possible definition of partial tracing the comb? Is there any possible alternatives?
You mean this step to remove the last?
Yeah, I mean, is there a better way of, or is there any other possible alternative to this approach?
Well, if you talk about partial trace, if you consider partial trace of the Troy operator, then this is the case. But for channels, you can discard. How to say, for an input system, you can feed that with any state, but this state could be fixed and known. Like you can control what input state you give to the input part. So that's a slightly different way to remove the input.
Okay.
Why assumption of bounded information loss is needed? This is due to the independent test. I guess sorry, let me clear this. Yeah, the general independence test is hard for mixed quantum states without low rank guarantee. So that's why we need a bounded information loss, which corresponds to the low rank assumption.
Okay, any other questions? Okay, if not, then let me thank Gerbai again for this very, very interesting talk.
Yeah, thank you.